To complete our discussion of conservation of momentum and collisions, we'll look at elastic collisions. We're going to look at this in three ways. First of all, we're going to consider elastic collisions themselves between two objects of any mass. Then we're going to look at two special cases. One where the two masses are equal in size, and the final case where one object has a much larger mass than the other. So let's talk about elastic collisions. In an elastic collision, two objects collide and bounce off each other. The momentum and the kinetic energy are conserved. None of the energy goes into anything else. So if we know the masses and any two of the velocities, these two conservation equations enable us to calculate the other two velocities. So in this case, we write two conservation equations. So again, looking at our before and after pictures, before we have object A and B approaching each other with momenta ma, va, and mb, vb. After they collide, we see them moving apart with momenta ma, va prime and mb, vb prime. So using conservation of momentum, we simply sum the momenta before and make that equal to the sum of the momenta afterwards. This is the common conservation of momentum equation that we've seen from the beginning. In addition to that, we have the kinetic energies. The sum of the kinetic energies before and after have to be the same. And if you remember, the kinetic energy is just given by 1/2 mv squared. So for object A, it's 1/2 mava squared, and for object B, it's 1/2 mb vb squared. So those together give us our kinetic energy prior to the collision. A similar pairing, similar sum, expresses the kinetic energy after the collision, where we've just substituted v prime for v in both cases to signify the velocities have changed after the collision. In the last slide, we saw two expressions. One was a conservation of momentum, and the other was a conservation of kinetic energy. These two equations can be solved simultaneously, and if we know any two of the velocities and both masses, we can find any two of the other velocities. But rather than getting too wound up in the algebra of doing this, what we'd like to do is just summarize this. So we'll look at the three cases we talked about: the general case of masses of any size, a case where one mass is much greater than the other, and a case where two masses are the same. So let's start with the general case. For all elastic collisions, regardless of the masses of the objects will separate after the collision with the same relative speed that they collided with. Now note that that's speed. So if they approach each other at 2 kilometers per second, then they will separate at 2 kilometers per second. The speed will remain the same, but the directions relative to one another will change. When we solve the equations simultaneously involving momentum conservation and kinetic energy conservation, we get this expression that the sum of the velocities of object 1 before and after is equal to the sum of the velocities of object 2 before and after. It's very simple to remember. So we've got v1 plus v1 prime equals v2 plus v2 prime in elastic collisions. This can be applied when we have a case where one object is much more massive than the other. In this case, the velocity of the smaller mass will be double, if you like, that of the mass it was hit with. But let's keep this even simpler than that. The main thing is that a large mass will be unchanged in its momentum. Something small will barely disturb its path. So what we can see is that if V1 is the large mass, then before and after is the same, so we get 2v1 prime. If the smaller mass wasn't moving to begin with, its velocity would be 0, and consequently we could see that v2, a small object hit by a larger object, is going to be going twice the speed of the larger object when it's hit. And that's what this diagram expresses. In the next case, we look at objects of similar mass. In the case where two objects have identical masses, they exchange velocities. And so we get that v1 prime is equal to v2, and v2 prime is equal to v1. So if you remember these three cases, you can solve a lot of problems involving elastic collisions. So although the derivation of an elastic collision is much more complicated than that of an inelastic collision, the equations that you can work with to find out what happens afterwards are very, very simple. In the last slide, we showed the elastic collision equations. V1 plus V1 prime equals V2 plus V2 prime. But where do these come from? This slide is only for those that are interested in that derivation, or for more advanced classes. So what we do is we start with a conservation of momentum and conservation of kinetic energy. A couple of slides back, we pointed out that these were given by these two expressions, that m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime, the conservation of momentum. And for conservation of kinetic energy, we see that we're adding the kinetic energies, a half mv squared, for each of particles 1 and 2 before and after. So again, you can see 1/2 m1 v1 squared plus a half m2 v2 squared is equal to a half m1 v1 prime squared plus a half m2 v2 prime squared. We can rearrange these equations. In the case of conservation of momentum, we can collect those terms involving particle 1 or mass 1 on one side and those involving mass 2 on the other. So we end up subtracting m1 v1 prime from both sides and m2 v2 from both sides. In the case of conservation of kinetic energy, we can eliminate all the 1/2s since it's in every single term. When we're done with that, we can rearrange the kinetic energy equation in the same way. We collect all terms to do with m1 on one side and m2 on the other. So we subtract m2 v2 prime squared from both sides, and we subtract m1 v1 prime squared from both sides, and we get this expression: m1 v1 squared minus m1 v1 prime squared equals m2 v2 prime squared minus m2 v2 squared. Now we can pull out the masses on both sides. We get these two expressions, one for momentum and one for kinetic energy. And now what we can do is combine these. What we can do is take the kinetic energy expression and divide it by the conservation of momentum expression. And here's what we see. On the on the left-hand side, everything is multiplied by m1, both in the numerator and the denominator. And similarly on the right-hand side, everything is multiplied both in the denominator and numerator by m2. Now we've done another trick, which is that we remember from algebra that if we have a squared minus b squared, that's just equal to a plus b times a minus b. And we've done just that here. We've taken v1 squared minus v1 prime squared and taken it into these two terms, v1 plus v1 prime and v1 minus v1 prime, and similarly for the other side, v2 prime plus v2 times v2 prime minus v2. So if we look above and below at the numerator and the denominator on each side, we can see that the terms involving the differences of velocity are eliminated, as well as the masses. And now we're simply left with the equation that we talked about before, which is v1 plus v1 prime equals v2 prime plus v2.